Okay, we're going to take a look at the following claim. Every ring is isomorphic to a subring of an endomorphism ring of an abelian group. This is pretty cool because it's a ring theoretic analog of Cayley's theorem. Okay, so we're going to start off by assuming that we have some ring. So let R be a ring. And we're going to assume that R has a multiplicative identity, so it has unity. And what we're going to do is we're going to define a map, and we're actually going to define a family of maps lambda sub R. So for every element R in our ring, we have a map sending some element X in our ring to R times X. So a left multiplication by R. Now, it's not too hard to check that this is a homomorphism of the underlying additive group of R. It's not really that hard to check at all, and I'll leave it to you, the viewer, to check if you want an exercise to do. Okay, so we're going to continue by defining another map, this one just called lambda, and this is going to be from our ring R to the ring of left endomorphisms of R plus, which denotes the underlying additive group of R, which is an abelian group. Okay, and what this map lambda does is that it sends some element R to its left multiplication map, so lambda R. Now, the natural question is this map lambda a ring homomorphism? So, is lambda a ring homomorphism? So what we need to do is check that it preserves the addition and multiplication of both rings. So we're going to check addition first. And so we're going to start off with some arbitrary elements A and B in our ring. So A and B are elements from our ring. And we're going to think about lambda of A plus lambda of B. Now, lambda of A was simply the left multiplication map by A, and lambda of B was simply the left multiplication map by B. And addition on our endomorphism ring is defined pointwise. So this map, lambda A plus lambda B, defines a map which sends some element X of our ring to A times X plus B times X. And we can use the distributive property of our ring to factor this. So this is the same as A plus B times X on the right. Okay, now we're going to take a look at, so what about lambda of A plus B? Well, this is going to send A plus B to the map left multiplication by A plus B. So lambda A plus B is a map sending some element X to left multiplication by a plus b, so a plus b times x. Well, this is exactly the same thing as lambda a plus lambda b. So we can see that lambda of a plus lambda of b is equal to lambda of a plus b. So it preserves the addition. What about multiplication? Okay, so we're going to think about lambda of a times lambda of b, except it's important to remember that we're in the endomorphism ring right now, and multiplication in the endomorphism ring is not defined pointwise. It's defined by composition of endomorphisms. So this is actually lambda a after lambda b, and so we're doing lambda b first, and lambda b is a map sending some element x to left multiplication by b, and we're composing this with lambda a. So lambda a after lambda b, this is a map sending some element x to, so it was lambda b first and then lambda a, so now multiplying on the left by a. So x is sent to a times b times x. Now, on the other hand, we could do lambda of a times b. What is this? Well, this is just lambda sub a times b, and this is the map. So lambda ab is the map sending x to left multiplication by a times b. So x is sent to a times b times x. Now, this is exactly the same thing as the map above. So, in particular, lambda a after lambda b, or I'm sorry, I should write it like this to be consistent. Lambda of a after lambda of b, this is equal to lambda of a times b. So lambda preserves the multiplication. We should also check that lambda preserves the additive identity. So does lambda preserve 0? And this is not really all that hard to see. So if we take lambda of 0 and think about this for a second, so this is going to be the map lambda 0, and lambda 0 is a map sending any element x in R to 0 times x, which is the same thing as 0. So any element in our ring gets sent to 0, and this is exactly the 0 map in the endomorphism ring. So in conclusion, lambda is a ring homomorphism. Okay, so we have this homomorphism lambda, which sends elements of our ring to the ring of left endomorphisms of R+. Now this homomorphism has some other nice properties. In particular, we're going to show that it's injective. So our goal right now is to show that lambda is injective. And we're going to do this by showing that the kernel of lambda is trivial. So what is the kernel of lambda? Well, if we think about it, this is going to be all elements R in our ring that get sent to the zero map of the endomorphism ring. So we want to find R in our ring such that lambda of R is equal to lambda 0. But what does this imply? Well, this implies that if we have some R in the kernel of lambda, that R times X, so remember that lambda R is the same thing as left multiplication by R. So this implies that R times X is equal to 0 for all X in the ring. So we can take any element X in the ring, multiply on the left by R, and the result of this is 0. And well, there's only one element in the ring that has this property, and that's 0. So in particular, we could take X to be 1. So if we take X to be 1, then this implies that R times 1 is equal to 0, which implies that R is equal to 0. So the only elements that can possibly get sent to the 0 map is 0 itself. And this implies that the kernel of lambda is trivial. So the kernel of lambda is just the set containing 0. And this implies that lambda is injective. And what does it mean for lambda to be injective? Well, it means that R embeds into the endomorphism ring. So this implies that R is isomorphic to lambda of R. So R embeds into the ring of left endomorphisms of R plus as the image of R under lambda, the homomorphism. And while the image of a subring is a subring, so the image of R under lambda, so lambda of R is a subring of ML R plus. So we've shown that the ring R is isomorphic to a subring of the ring of left endomorphisms of R plus. And R plus is just the underlying additive group of R. And this completes the proof.